Welcome to the AI Research Roundup. I'm your host, Alex. Today is May 11th, 2025. We're discussing an ICLR conference paper published just under 4 months ago, MOS, Model Synergy for Test Time Adaptation on LiDAR-Based 3D Object Detection. This paper tackles how AI using LiDAR, a laser mapping tool for 3D object detection, can struggle with new data, a problem called domain shift. The authors introduce Model Synergy, or MOS, a new online test time adaptation, or TTA, framework. Test time adaptation allows models to adjust during actual use, and this paper's Model Synergy approach does this by cleverly blending knowledge from past model versions to handle these shifts. Alright, so this figure visually lays out the problem the researchers are tackling. It illustrates 3 main types of domain shifts that can degrade performance. First, we see cross-dataset shifts. For instance, when an AI trained on data like Waymo encounters different object characteristics or sensor setups in KITTI. Second, there are corruption shifts, such as foggy conditions or motion blur affecting the LiDAR data. And third, the particularly challenging cross-corruption shifts, where both these types of changes occur simultaneously. This comprehensive look at shifts, especially cross-corruption, is key to what Model Synergy addresses. Building on that understanding of domain shifts, this figure then illustrates how current test time adaptation methods actually fare, especially since many were designed for 2D tasks. The plot shows performance using AP3D, that's average precision for 3D object detection, a score for accuracy, when a model trained on new scenes is applied to KITTI. We see existing test time adaptation approaches, like tent shown by the star, and kata, the green plus symbol, show limited gains. In contrast, ours, the Model Synergy method marked by the orange X, performs significantly better, even nearing the unsupervised domain adaptation, or UDA, baseline which adapts using unlabeled target data beforehand. Okay, so how does Model Synergy actually achieve these impressive results we just saw? This figure really clarifies its core mechanism. We see a model bank at the top, which is essentially a library of past model versions, or checkpoints. As a new target data batch, like XT+1 comes in, Model Synergy dynamically assembles what's called a supermodel. It does this by combining information from selected checkpoints, each given a specific synergy weight. These weights, like the 0.05 or 0.50 shown, are crucial. They prioritize checkpoints offering unique, non-redundant knowledge, effectively tailoring this supermodel to the current data. So building on how those synergy weights are determined, this figure details the overall workflow of Model Synergy. It kicks off with a, quote, warm-up phase, where initial models are self-trained on early data batches, like X1 to XK, and then saved into the model bank, that's F. Then, the core Model Synergy step happens. For new incoming data, it draws from this bank, applies those crucial synergy weights to assemble the supermodel, and uses its predictions to self-train the current model. Finally, Bank Update keeps the model bank fresh by adding the latest adapted model and removing the one with the lowest average synergy weight, ensuring efficiency. Alright, so now we get to the hard numbers. This table presents the results for test time adaptation in 3D object detection across different datasets. It uses metrics like average precision from a bird's eye view, or AP_BEV, which measures accuracy from a top-down perspective, and that average precision for 3D object detection we talked about. For the Waymo to KITTI shift, Model Synergy, or MOS, really shines, achieving 64.16% on average precision for 3D object detection. This performance closes nearly 80% of the gap to the Oracle. That's the ideal score if the model was trained directly on the new data. Okay, so after seeing its strength in cross-dataset shifts, this table now shows how Model Synergy performs when facing various data corruptions. This is the KITTI to KITTIC scenario. So, a model trained on clean KITTI data, tested on versions with heavy fog, snow, or motion blur. Looking at the average precision for 3D object detection scores, Model Synergy, or MOS, consistently outperforms other test time adaptation methods like tent and kata across nearly all corruption types and difficulty levels. Its strong mean performance really underscores its resilience to these real-world data issues. So, to wrap things up, this model synergy approach is a really promising way for AI models to handle the unexpected in 3D object detection, especially for systems using LiDAR, which is that laser-based scanning. It shows strong results adapting to new datasets and various data corruptions, even those tough cross-corruption scenarios where both types of changes happen at once, by intelligently combining knowledge from past models. While it's quite effective, there's a bit of computational overhead. That's all for this AI Research Roundup. Thanks for tuning in.